Okay, here's another problem with net torque and producing an angular acceleration. In this case, there'll be first one object, which makes the problem fairly simple. But then if you add another object, the purpose here is to show you that moments of inertia are summative. So if you have several objects that are attached together, you simply can add together their moments of inertia. So you've got like the person who is going to push the merry-go-round and start it spinning at a perpendicular angle, so you get a maximum angular acceleration. And what's going to happen here is he's exerting a force of 250 newtons at the edge of the wheel, okay, or edge of the, in this case it's a disc. So we can treat the, it says here we can treat this merry-go-round as a uniform disc with no friction. So notice that for a disc, if you look up in a table, the moment of inertia is 1/2 mass of the disk, radius of the disk squared. Now, later on in the problem, in part B, they're going to put a child on the ride out at a distance away, and the child would be a point mass, and the moment of inertia for a point mass is mass of the point times the radius of the, where the position of that mass is squared. All right, but let's do part A first. So again, what we want here is just the net torque equals I alpha. So the force of pushing is 250 newtons out at the edge of the ride, which is 1.5 meters away, and the mass of the ride is 50 kilograms. So the first part of the problem, we can just use torque equals I alpha. There's only one torque, and it's just the ride itself. So we have RF sine theta equals 1/2 mr squared alpha. Okay, again, moment of inertia of a disk. Substituting in the numbers given in the problem, pretty easy from here on out then. So the key idea is where do we get that I, right? So the angular acceleration of the ride ends up being 6.67 radians per second squared. Now what happens when you add some mass? Well, you're going to increase the rotational inertia because, number one, you've increased the mass, but also its position has an effect as well. Where the rider would sit on the ride has an effect on how hard it is to spin. So just like mass, rotational inertia is summative. So the total moment of inertia in this case, once the child is on the ride, will be I for the ride plus I for the child. It's not a vector. We don't have to worry about pluses or minus. It's just a summative quantity. So we have the moment of inertia of the ride plus the moment of inertia of the child. And the child can be treated as a point mass. Okay, so that's how we can come up with the total moment of inertia and just apply the equation again. So the only thing we change in the problem in this case is what happens to the moment of inertia. Since we're going to increase the moment of inertia, we're going to expect that we'll decrease the angular acceleration because for the same torque, it offers more resistance to changing the angular velocity. And so what we see in this case is when we add the child, located 1.25 meters away from the center, that has a net effect of decreasing the rotational acceleration or the angular acceleration to 4.44 radians per second squared. Okay, so an increase in rotational inertia causes a decrease in angular acceleration for the same applied torque. But that's how you deal with summing up moments of inertia.